Welcome to Demystifying Math. In this lesson, we're going to be discussing limits. To find a limit of a function is to find the y value that we call L that the graph approaches as x approaches a specific number c. We write this as a limit as x approaches c of f of x equals L. Let's start with a specific example. Suppose we have the graph of x squared plus 1. Well, you know that that is a quadratic function with a vertex of the ordered pair 0, 1. You also know that any of the polynomial functions are continuous smooth curves and defined over the entire real numbers. So for this particular problem, as x approaches 2, we're also closing in on y equals 5. So our limit would be 5. But of course we could have found that pretty easily by just plugging the 2 into the function. So we would have 2 squared plus 1, which equals 5. This is called the direct substitution method. And the direct substitution method works because the function is both defined and continuous at our c value, in this case at x equals 2. For functions that are not defined at x equals c, we will need to use some other techniques. For instance, with this function, we have x squared minus 4 over x minus 2. If you tried to plug a 2 into the function, you would get 0 over 0, which is indeterminate and doesn't help us in any way to figure out what number the graph is approaching. Go ahead and try to type this function into your graphing calculator. Now when you did that, you should see a straight line, and your graphing calculator probably connects it so you can't see like a big gap in your line. But if you try to evaluate the function at 2, your graphing calculator should give you a non-answer. But I got 4, and I got 4 by simplifying my fraction. So I have x squared minus 4 over x minus 2, and I factored out the numerator. And when I did that, the x minus 2's canceled. So I'm left with the graph of x plus 2, which is a linear function with a y-intercept at 2 and a slope of 1. Now these are equal functions everywhere except where x equals 2, because the new function is defined at 2 where the original function was not. So you should make a note and say, well, x squared minus 4 over x minus 2 is equal to x plus 2 with a domain restriction such that x cannot equal 2. Okay, but if I wanted to figure out where that gap is in my graph, I would plug 2 into the new function and I would get out 4. Now, 2, 4 is an open circle or a gap in the straight line that we have there. So what we want to do now is evaluate our limit as x approaches 2. Well, as x is closing in on 2, y is closing in on 4. So our limit here is 4. Okay, so what we just did was called the dividing out technique. We divided out a factor so that we could simplify it, find another function that's similar to the original function we were given, but defined at the x value that we have in question, in this case at x equals 2. Now, this dividing out technique works because the limit from the left side and the limit from the right side are approaching the same y value. If that doesn't happen, then we're not going to have a limit. It's not going to exist. Let's look at that. If your two one-sided limits are not equal, then you would say that the limit as x approaches c of f of x does not exist. Let's look at this particular problem. If you plug a 2 into the function, you're going to get out 0 over 0. If you plug in any numbers less than 2, you're going to get out negative 1. If you plug in any numbers greater than 2, you're going to get out positive 1. So your graph looks like this. And if you look at your limits from the left, you're going to get negative 1, because we're approaching negative 1 for our y value. If you take the limit from the positive side, you're going to be approaching positive 1. So, since our two limits from each side do not equal, they're not coming into the same number, we would say that the limit does not exist. Okay, if your graph heads to infinity or negative infinity as x approaches c, then the limit does not exist. Let's take a look at this example. We have 1 over x minus 2 all squared. Now again, you can put this on your graphing calculator and look at it. But what you should know is that you have a vertical asymptote at x equals 2. And by definition of vertical asymptotes, you're going to have both sides of your graph approaching either infinity or negative infinity on each side of your vertical asymptote. Now in this case, because we have a squaring function, everything's going to be positive. So both sides are heading toward positive infinity on both sides of that asymptote. So as we close in on 2 from the left side, the graph is going to infinity. As we close in on 2 from the right side, we're heading toward infinity. So our graph is heading toward infinity. But remember that when you're looking for a limit, you're looking for the bound of the graph. And since this graph is unbounded as we go into 2, we would say the limit does not exist. A lot of people would just say it goes to infinity, which is true, but that's the same thing as saying it's unbounded. So we have no limit. All right, our next technique that we're going to talk about is the rationalizing technique. And again, what we're doing with these techniques is trying to find a similar function, but one that's defined at the c value. In this case, we're looking for the limit as x approaches 0. And if we plugged in 0 into our function, we would get 0 over 0 again. So that's not going to help us. So what we're going to do instead is try to rationalize our numerator. All right, so here's a picture of the graph. Again, you can look at it on your graphing calculator, get a feel for your graphs. But this one is a nice smooth curve with an endpoint at -9, because you can't put anything less than -9 into the radical. But it also has a gap at 0. What we want to do is figure out what that y value is as x heads into 0. So let's go ahead and try to rationalize our numerator. What we're trying to do by rationalizing the numerator is get rid of that 0 over 0. Okay, so we're going to multiply numerator and denominator by the conjugate. The conjugate is the same thing that we had, but we're going to change the sign in between the two terms. So we're going to multiply numerator and denominator by the square root of x plus 9 plus 3. And then FOIL the numerator. So our first terms, when you multiply the square root of x plus 9 by itself, you get x plus 9. And for multiplying the last terms together, we get -9. The inner and the outer terms are going to cancel each other whenever you multiply by the conjugate. Then I just multiplied across for the denominator. Now simplifying our numerator, we just end up with x. So now our two x's are going to cancel each other. And we're left with this new function, which is 1 over the square root of x plus 9 plus 3. And this one is defined at 0. So now what we can do is evaluate it using that direct substitution method. And we get 1/6. Now remember, the new function, the old function would have the same domain, so you would restrict it so it's not equal to 0, but go ahead and plug it in to evaluate the limit, because remember, the limit is what we want as we close in on 0 for the original function. Okay, let's go back to our graph and see that this is actually 1/6. Okay, so that gap that we have in our graph at 0 is just below 0.2, which looks like it is at 1/6, close to it, as we close in on 0. And you could probably verify that on your graphing calculator just by using your trace key and closing in on 0. Let's go ahead and make a table of values and see that our graph actually is closing in on 1/6. So let's find some y values for x values that are very close to 0. So I'm going to start off with -0.1 and +0.1. And I get these two output values that are really close to 0.16 repeating. Let's try to go in a little bit closer on each side. And again, we're getting a little bit closer to 0.16 repeating. Let's go in a little bit more, and we're almost there. So you can see that you can verify your answers pretty easily just by plugging a few numbers really close to the C value that you're looking at, and that will help you to make sure your answers are reasonable. Thank you for tuning in to Demystifying Math.